second to find the slides and share my screen. This meeting is being recorded. I know. Second. Okay. Okay. Right. Okay, let me share my screen. Go back here. Okay, so today's lecture is again on data structures, similar to what we started last week. Yeah, on Thursday. But we have done part of this lecture already because we were fast on Thursday. So these string-like types we have already done. So let's see how far we get today. And first topic is about arrays. So you have arrays in Haskell as well. I mean, last time we talked about this, that lists are not suitable for everything. So in particular, random access is bad for lists because it's linear. If you want to find the 25th element, you always have to start at the head of the list and go all the way until you reach that element. So if you need fast random access, lists are certainly unsuitable, at least long lists. And we looked at maps and also sequences. And sequences in particular for random access are very good. So they only have like logarithmic access time, which is almost as good as constant. But sometimes you really want arrays where you have constant random access time and where also the memory representation is extremely compact, where it's just a continuous region of memory. And Haskell has that. And it has had that like forever in the array package. But in this lecture, we'll concentrate on a more modern one that's called vector. However, I must say, I personally I like array, and it has some advantages over vector. So vector is only for one-dimensional arrays, and they always start at index 0, like in most programming languages. So arrays always start at 0, the index. Array is much more flexible, so you can start at whatever index you like, and it can also be higher dimensional, so it doesn't necessarily need to be one-dimensional. But nevertheless, vector is very nice, so we'll look at that. And first talk about, or maybe we should just look at some code actually, and also on the internet. We just go for vector package. So you can easily find it on Hackage. It's called vector. Okay. So, right. And let's also look at some code. Okay, sorry, I was just looking at the next lecture. Right. So that comes later. So now we're in this one. Right. So let's just import this data.vector. And let's do open a REPL. Okay, now we should be able to do what's here on the slides. So first of all, in order to get a vector, we have from list. So let's see from list. Okay, we don't, it seems. Pretty sure. Let's see. From list. Yeah, it's actually available. I think in GHI I just have to load this module. Now we should have it. Yes. So from list, as the name suggests, takes a list and returns a vector with the elements the same. So what was the example on the, on the slides? 1, 2, 3, 4, 5. So I can do, for example, oh yeah, and we see that it is displayed like a list. So the show instance just uses that from list, but it is indeed a vector of ints now. And one of the operations we have is this slash slash. So if we look at type of that, so it takes a vector and a list of tuples of ints and a's and returns a new vector. So this updates the vector. So this list of tuples is index and new value. So if I want to change the 2 to a 20 and the 4 to a 40, for example, I could do v slash slash. So the 2 has index 1 because it starts at 0. That would be 120. And the 4 has index 2, 3. So 3, 340. And then I get this new vector with the values replaced. And again, as before, we by default use persistent data structures. So the old vector is still there, untouched. So this slash slash creates a new vector. So it doesn't modify anything in place. And that's something you have to be careful about, because in order to achieve that, so a vector is really basically a pointer to some like contiguous block of memory. And if we now do some update, then we have to copy the whole array to a new block of memory because we still want the old one to be around. We don't change anything in place. So this is a very costly operation. So normally if you need updates, it's a bad idea, or if you need a lot of updates, it's a bad idea to use vectors. But random access is indeed a constant time. So this is good. And I think it's exclamation point. So if we ask for the type of that, yes. So if I have my v, I can ask for, I don't know, the element at the third index, and it gives me 4. And this is, as I said, constant time. So that's where vectors shine, at random access, but not at update. And if you need to update something and you want to use persistent data structures, then what we looked at last time, like finite maps or sequences, are much better. Finite maps, for example, have logarithmic update time. So it's not constant, but it's far better than linear. So arrays are mostly useful if, I mean, these persistent arrays, if you have something that doesn't change much or it doesn't change at all, like some sort of lookup table or so. And this is just an overview of available functions operating on vectors. So we can generate an empty vector in constant time. This is a function to generate a vector. So we give it the length of the vector and the function that tells it what the element at each index should be. So we can try this out. So we could get our original one again with 5. So I want length 5, and at index I want I plus 1 to get the same as we had before. Right, so this says I want a vector with 5 elements, and at index I, the element should be I plus 1. So at index 0, it's 1, and at index 2, it's, sorry, at index 1, it's 2, and so on. And at index 4, it's 5. So that's one way to generate a vector. We saw this other way from list already. It just converts a list into a vector. We can concatenate vectors, but we see the complexity is very bad. So it's even worse than for lists. So we could do v plus plus v. Okay. And this again shows, I mean, I mentioned that before, normally it's a bad idea to, I mean, for certain libraries to just import them. And vector is one of them because a lot of lames here, like the plus plus, clash with something in the prelude. So it would probably be better to import this qualified and then, for example, as v. So we can reload. Now, of course, I must qualify everything. So the generate, for example. And now it should work. So v plus plus v. Right. So this concatenates two vectors, but it's horribly slow. I mean, this is basically the selling point of vectors, that random access is so fast. There's also a safe version. So if I do, for example, take my v and look at index 5, which doesn't exist because the highest index is 4, it crashes and I get an error. If, however, I use the exclamation, sorry, that was, I must qualify with v. So I get an exception out of bounds. And there's the safe version with the question mark. So in that case, I just get nothing. And if I use an index that does exist, I get just the value there. Slice takes a start index and a length, and then gives me that slice of the vector. So again, in our example, if I have slice, let's say I start at index 1 and want 3 elements, then I get those 3. And interestingly, that is also constant time. So slicing is also fast for vectors. This update // we already said is very slow. Then we also have a map. So actually, if we look for information on vector, which I need to qualify now, but in this case, normally what one does is, I've shown that before with map, for example, is that one has 2 import statements, and some things one imports unqualified, like the name of the main type. Let's do that. So if I ask for information on vector, I see lots of instances of type classes, in particular functor, even monad. It's basically the same monad instance as for lists, because I mean, from a logical point or a semantical point, vectors and lists are the same. It's just a collection of elements. I mean, there are some differences. For example, lists, as we know, can be infinite and vectors cannot. If you try to generate an infinite vector, it will just hang or crash. And so vectors always have like a well-defined length. And of course, the performance characteristics are different for vectors and lists, but like semantically, it's the same thing. Therefore, it makes sense that it's also a monad, and in particular, functor. So if I define my vector again, this one, and now I can, for example, fmap, whatever, times 100. So that works. Okay, and we also have like other functions that we are used to from lists. Filter, for example, or fold right. But again, they are not efficient, so are not more efficient than for lists. Because in order, for example, to do a filter, again, we need to go through every element in the vector, and we have to create a new like block of memory for the result. But it should work. So if we filter, for example, for odd elements in our V, we get just the odd elements. Okay, so that's vectors. And actually under the hood, they are implemented in terms of these arrays that we don't look up in the lecture. But they are quite primitive and directly built into GHC. And then it also stores lower and upper bound, so that's to make this slicing efficient. Right, and if you look at the website again, you see at the main page of the vector package, you see there are lots of flavors of vectors. So for example, there's also something called vector mutable and something called vector unboxed. At the moment, until now, we have only looked at these vanilla vectors here. So let's talk about the unboxed stuff first. So, and as the slides suggest, let me just ask for information on the type int. And I think in the beginning we said ints are like primitive built-in types. But if you look at the definition here, it looks as if they are not. I mean, it's just data int, just another data declaration of a data type int. And there seems to be this weird constructor I hash and an argument of type int hash. So it seems int is not really primitive. And okay, I mentioned that. So what's an int hash? And in order to even get that, so if I ask for information, GHC prim int hash, then I get a parse error. So Haskell doesn't handle hash as well, the parser for Haskell. So in order to actually even do this, you have to activate an extension, which has the quite mysterious name magic hash. I reload and ask again, then I think I must activate the extension in GHCI as well. So magic hash. Oh, sorry. Okay, now it's better. It's not a parse error anymore. It's just right. It's just that it doesn't find this GHC prim. So let me import that as well. Hope I can.
Maybe
I can't. It's yeah. It's in some other package. Let me just add that. Let me reload everything. Go back here. Okay. Okay, now I do get, I'm sorry. Okay, but this looks already better because now this GHC prim works. I mean, maybe for good measure, I should also do the types. Just to get rid of the clutter. Okay, so this looks now nice. So int is I hash of int hash, but we wanted to know what int hash is. I again have to, in GHCI, also set this magic hash thing. Okay, finally. And now we see we don't get, I mean, it just says int is int without any like definition. So this int hash is really primitive. So that's built into the compiler. And int hash, so that's this here, is a so-called unboxed integer. And that's really basically like close to the metal, just a machine integer. So it's just bits encoding integer. And we know that for other Haskell values, for normal Haskell values, it's not that easy because of laziness. We talked about these thunks. So values can be unevaluated. So there's just a thunk, like a pointer to some piece of code that on demand can compute this value. um, so the normal int is so-called boxed integer, which has one additional layer of indirection. So instead of directly pointing to a bit encoding of an int, it's a pointer that can either point to an unboxed integer or it could point to a thunk that on demand computes this int. So unboxed ints have some advantages. There is no indirection, so they are faster and they take less memory because it's just the 64 bits these days that you need to write these bits in memory. But on the other hand, boxed ints that we have used until now, they admit laziness and all the polymorphism normally that we have seen so far only works over box types. So all the types we've seen until now were always these boxed normal types. And it's very rare that you actually have to deal with these so-called unboxed types. It's just like for certain scenarios where you need every inch of performance. And there are actually also literal syntax for them. So let's see whether that works. Okay. Maybe I must just ask for the type. Okay. So there is a built-in syntax to get these unboxed ints with the hash afterwards, and it seems there's more. So with 2 hashes, I get a word, and with if I have like a decimal point, with 2 hashes, I get a unboxed double. With 1 hash, I get an unboxed float, so single precision. And we even have unboxed characters. So, right. So some of these primitive types are actually like, I mean, they exist in a built-in version with this magic hash at the end, which are then just like directly in memory encoded things. No indirection, no laziness, no funcs. We also have operations on them. So this plus hash or this plus hash hash. Plus, so we can add them, and I assume there's similar things for multiplication and so on. Actually, let's see. Yeah. Okay. So far, so good. And if we ask for the kind, so if let's just as a quick reminder of last time, if I ask for the kind of int, it's of kind star. We said that everything that's inhabited in Haskell, everything that has a value, so types that have a value or potentially have a value, like int and lists of strings and basically everything, have kind star. And other things like maybe, for example, just a naked maybe, it's not of kind star because it's of kind status star. That, which tells us, sorry, kind, which tells us maybe first needs something else of kind star to become of kind star. So then, I mean, a maybe, there's no value of type maybe, but there is a value of type, for example, maybe character. Anyway, so that's what we said about kinds so far. But now if we ask for the kind of int hash, we would have expected star, I suppose, because it's like an inhabited type. They can have values, but we get this weird thing, type int wrap. And let's see. So we can also do word hash and float hash and double hash and character hash, I suppose. Which interestingly has the same kind as word. So it seems a character is just a word in memory, which sort of makes sense. Anyway, so we get these weird kinds. And star actually is a synonym for type pointer rep lifted. So our star, which we have dealt with in the last weeks, so types of kind star, they actually have this kind, but there are for these unboxed types, there are these other kinds. And yeah, okay, so these things are just like parameters to this type thing, this capital type thing. And normal polymorphism, I mean, that's one of the most important features of Haskell. For example, the identity function that goes from A to A and just sends an X to itself. This is actually an abbreviation. We mentioned that briefly when we talked about the extension scope type variables for all A of kind star A to A. So that means if I do, I mean, it, for example, C character, I get that. But if I ask for the type of it, the hash, then I get an error. And the explanation is on this slide. So normal polymorphism like this, it always implicitly assumes that A is of kind star. So, and int hash is not, as we just saw. Int hash or character hash, they are of these weird kinds. So polymorphism doesn't work for these unbox types. So we can't even apply it to it.
Lars, we
Yes,
have a question.
yes.
What does it mean that boxing makes all types look alike?
Well, I mean, they're basically all just a pointer to something. So it's always a pointer. And you can just pass around this pointer and operate in it. I think that's what it means. So I mean, they all take the same space in memory, and yeah, it's just a pointer, one pointer. And then to what it points depends on the actual type, or can depend on the actual type.
Okay, that was the one. Thank you.
Okay, okay. Right. And so normally we can't use these unboxed types for things like identity, for example. So I showed that doesn't work because it expects something of a type of kind star, whereas 3hash has type int hash, which has a different kind, this weird one. But there are some exceptions. So if we look at this dollar sign, for example, which we know is just another way for name for function application, and which is useful to avoid parentheses, then we don't see anything, which is interesting. It's a bit depressing.
Maybe you have to activate scope type variables extension, or
Yeah, let's see. Kind signatures, maybe kind signatures.
nope.
Nope. Maybe they changed that recently.
Maybe.
Let me check in base. Second. Base. Catch. No, that's not what I wanted. That says, sorry, that's
in Google, maybe.
yes, but I think there. It still seems to be right. So basically, okay. So here, I mean, it looks as if it should be okay, right? If this is the right version of base now. So normally it would just so this B can, I mean, we saw this weird type thing now where we said that our star is just a synonym for type pointer rep, but here it's polymorphic in whatever this is. So dollar, for example, should also work for everything, including int hash. And there's an example here. So for example, we could write a function unpack. Let's try this. Okay, let's try this. It's called unpack int, yeah. So a function from int to int hash. So that at least compiles. Okay, fine. And now this example on the slide. So I can do I hash unpack int $3. Right, and that works, even though that I mean this is a stupid example. It would be better to have it here. I'm not really convinced by this example. I'm a bit confused. Let me just check this here, this base library. What base? That's 418, but we use for something else, right? We use
I'll check.
416. Yeah, sorry, what do you know?
I'm checking.
I think 416.4 or something.
Let's see. Yes, it's the previous one. GXC.
But that should also work.
But
I mean,
I think the actual it didn't change the functional application operator between versions.
right. But why does this not work then? I mean, this is not really surprising to me that this works because, I mean, 3 is anyway normal int. Why wouldn't it work? So I don't really understand the slide now. I mean, this is just a normal 3, an int. I mean, it would be interesting if you could use a dollar here.
Yeah.
And it seems you can't, which confuses me because maybe what polykines or something.
It still expects a lifted type. So,
Well, it does say here, I mean, only the B is special somehow. So the A not. Maybe the A still has to be of kind star. That could be. I mean,
right.
if I ask for the
You can ask for the type and not wrap it again. It should work.
see what's the kind of int to insta. I don't understand why this doesn't work then. What's the kind of type of unpack 3?
Unpacking.
I mean, I don't understand why dollar gives me this.
Yeah,
Whereas in the
I was
documentation it says it's that.
I'm thinking that maybe it's GHCI magic. So if you define it in the actual file in my work.
You mean I give the implementation like this?
No, I mean to actually write it in the
Oh,
file outside GHCI.
okay, yeah, okay. I hash. No.
No.
I mean, everything this slide says is true. I mean, this works. I just don't find that very surprising because, I mean, the 3 is anyway nothing weird. So it's a bit strange. But anyway, so it's
But
strange.
it returns, but wait, and back int returns, and that's the B, right?
Right.
So I mean, it follows it's not the A, it's the B, so it should work only on that case.
But I mean, in our case, the A is I hash. I mean, I hash. We apply.
No, in our case, in the slides case, A is int and B is int hash. So I mean, I think that's
Oh, no,
right
no, but hang on. Really?
because it returns.
Oh, yeah, you're right. Hang on. Yeah, yes, you're right. Yeah, I was confused. Exactly. That's right. A is, yeah. The function is this unpack int. So, and unpacking goes from int to int hash. So the result type is, yes, that's right. The result type is int hash. And
Yeah.
that works because for B is special. So the result type can be something special. So that works. Yeah. Thank you very much. Yes. So this works because the result type, this int hash, dollar works for all result types, not just for star. But I can't put the dollar here because now the result, now the function type is, I mean, the argument type is weird, but the argument type must still be star. So only the result type is special for the dollar. And therefore I can't put the dollar here, but I can put it there. So yeah, slides are fine. It's just, it's a bit strange, but whatever. But I never in my life had to worry about this actually.
Yeah, and we have a question as well.
Yes.
I didn't quite catch why it's called Levity polymorphism.
I think I also don't know, but I assume that this thing here, this R, is called levity, whatever. So I mean, normally polymorphism means that it's polymorphic in types, but all the types have to be of kind star. So I mean, polymorphism, if you write something, whatever, like, I mean, this is probably bad, but anyway, something like this until or so. So this is polymorphic in A, and that, I mean, it's normally polymorphic in type. And there can be more than one type parameter. Let's just go to some arbitrary place where there's like this map. I mean, this is a normal polymorphic function, and it's polymorphic in the types A and B. But what we haven't mentioned until now is that this can't be like arbitrary types. It must be types of kind star. And all the types we have seen until today have always been of kind star. I mean, the types that are inhabited that can have values. Right. And it seems that this thing here, so what we saw, that kind star is just an abbreviation for type some specific R, this pointer rep. That was this slide here. What was it called? Pointer rep lifted. So normally polymorphism only works for types of kind star, which is an abbreviation for type pointer rep lifted. And it seems if you make something even more polymorphic in the kind itself, in this kind argument, so it can also be int rep or word rep or double rep, and that is called levity polymorphism. I don't know why levity, but I assume that this argument basically is levity. So it's even polymorphic in that. Normally, when we say polymorphic, it's only polymorphic in the type itself. Can be anything of kind star, but it's not polymorphic in the kind. So the kind always has to be this type pointer rep lifted. But in these special cases like the dollar operator, even that it's even more polymorphic. So you can even use it for these things like int hash and word hash. Does that make sense? But where the name comes from, I have no idea why it's called levity. And maybe, yeah, maybe, I mean, levity is something with levitation, right? And it's lifting. So, I mean, these box types, they are lifted types. So maybe levity is whether it's lifted or not. So unboxed or boxed. And levity polymorphism means it works for both unboxed and boxed types. Whereas normal polymorphism only works for boxed types, which are the normal types that we use every day. Yes, that's, I think, why it's called that. Hope that answers the question.
Yes, it says thank you.
Right. And luckily I never had to worry about that, I think, in my life, except when teaching this specific lecture. Normally you don't have to. First of all, the optimizer, GHG has a powerful optimizer, is good at doing that automatically. That way it makes sense to use unboxed types under the hood. And there are libraries like vector library that we are looking at the moment, where you can work with unboxed values without having to deal with them explicitly. And finally, there is a specific pragma, this unpacked pragma, where you can say that certain like arguments for constructors or fields in a record should be unboxed. But then you can still work with them as if they were not. I mean, you don't need to use this hash stuff. It just tells the compiler it should in memory represent them without this additional indirection. And we briefly saw an example of that in the last lecture when briefly showed the implementation, the internal implementation of map as a balanced tree. And therefore, performance reasons, we were caching the size, I think, of the map of a node, basically, how many leaves there are. And that had this unpacked pragma. So that means that in memory that will always be unboxed and not a thunk or this indirection. But just by adding this pragma, you get this memory benefit and you don't have to juggle around with ihash and these hash stuff. So for those reasons, it's basically never necessary to know anything about this or to do anything about this. Right, and as an example of point 2 here, that libraries offer good abstractions. The vector library is one example for this. And there's a data vector unboxed module. So that works if the elements in your vector are actually types that have an unboxed version. And so then they are more compact in memory. So they take up less space. But they are also, you can't do this for arbitrary types because not all types have an unboxed version. I mean, we saw these primitive types, int, word, float, double, and character. And as we will see in a second there, I mean, it's not just restricted to those 5, but it also just doesn't just work for anything. So if you have a vector of our trees, for example, our tree type, then there is no unboxed version. And actually, in order to make that precise, there is this, unbox class. I think that defined by vector, which says which types you can use in these unbox vectors. And the ones we expect, so they are like these primitive ones, int and float, double, character. There's probably also word, I assume. And then there are also, as I said, it's not restricted to primitive types. There's also an instance like this. So if you have 2 unboxed types, then pairs of those are also unboxed. And the way you can think of it is, I mean, for example, if you have a pair of an int and a float, and then a vector of pairs of ints and floats, then I assume that in memory it will be actually 2 vectors, one int vector and one float vector. that are the same length, and that's how this is basically implemented. So under the hood, I mean, basically you only have these primitive types, and other types that you can build with from those, for example, with pairing, that then also works by just having several copies of these vectors. I mean, not copies, like several vectors in parallel, basically for the various components of your pairs. And the interface is basically the same as before. It's just more restricted. For example, I mean, this is now not functor anymore, because both the element type and the result type now have to have this unbox constraint. So map doesn't any longer work for arbitrary Bs, but only for Bs that can also be unboxed. Similar for, no, not similar. So that's basically it, yes. So, I mean, it's basically the same thing, except that you have this unbox constraint everywhere. So if you have like a vector of ints, for example, then you can use the unboxed version, and it takes up even less space, and it's maybe even a little bit faster still. But as you see here in this API, nowhere is there a hash. So you can just work, I mean, with the normal Haskell types as before, A, and only internally in memory, those A's will then be unboxed and saved much more compactly. Okay. So, right, so this is actually just a library. So you have this high-level interface to it. And as I already hinted at, so there's an appropriate implementation, how these are actually implemented, how they are then laid out in memory. As I said before, so probably an unboxed vector of pairs of ints and floats will probably be represented as two vectors, one int vector and one float vector that are like in parallel. Okay, and that uses something under the hood called data type families, which we haven't looked at and probably also won't in this course. So that's some more advanced type level thing you can do. Right. Are there any questions at this point?
Not so far.
Good. Okay. So finally, we also have mutable vectors. And I think if we go back here, so we have, this was the original one I showed you, the vanilla vectors. Then we have here the unboxed ones. Now we are looking at mutable vectors. And I think in the slides, we don't talk about them, but you also have mutable unboxed ones. So yeah. And there are some algorithms that actually can only be implemented if you can mutate data structures. I mean, at least efficiently. And actually, that's fewer than one thinks. I think if somebody comes new to functional programming, in particular Haskell, with all these persistent data structures, people think they will have to sacrifice a lot of speed because they don't understand how persistent data structures work. But actually, most common algorithms that have like that you typically or that most people would implement using mutable arrays or other mutable data structures can be implemented just as efficiently using persistent data structures. But there are some exceptions. So sometimes if you want a full efficiency, time complexity, the best known one is actually algorithms that really need to mutate. And we have already seen examples of mutable data types in Haskell, like IO-refs, TVARs, and MVARs. But there's also, in the vector package, there's this type of mutable vectors. And it's similar to what we have seen for IO-refs, except that now it's for vectors. So let's maybe just try it out. So that's data.vector.mutable, I think. IO vector. I don't know, I could also still call it V, but maybe let's call it IOV. Okay, let's reload. So what's IOV new? Okay. So we can ignore this prim monad for a second. And so we can think IO. And so this looks a bit complicated, but it's basically just what it says on the slide here. So new, I just give the length of a vector, and then it will give me a vector of that length. I'm not sure how that's initialized, so probably not at all. Let me see. Let's look at construction. So not sure what the like default element here is. Doesn't say. Oh yeah, but replicate, for example. So replicate creates a mutable vector of the given length and fill it with an initial value. So that's, for example, we can use this. This is also here. So let's say V, and now I'm in the IO monad, so I can say IOV replicate. Now what comes first? Okay, the how much? So let's say, let's go again with our original example. So length 5. Let's first initialize it with zeros. Or I can also do 42s. Okay, so there's no show instance, but I mean, the operation worked. And now I have read and write to look at elements and write to them. So if I read v index 0, why?
I think might be clashing with the base read. You're using
Oh
the
yeah, yeah. Sorry. Of course. I must qualify it. Right. So this works. 4 should also work. 5 should give me, yeah, because index out of bounds. Okay, so this V now has 42s at each of the 5 positions. And now I can actually also write. So I can now say IOV write vector index, let's say index 3 and whatever, 9. And this is just IO unit. So I mean, I don't get a new vector back. I have now really mutated the V. So if I do this again, so actually we can do, no, okay, fine. So 0, 1, 2 are still 42, but now index 3 indeed has the 9. So now I have really mutated that vector for still be 42. So this IO vector behaves like you would expect an array, a normal array in an imperative language to behave. So it has like same performance characteristics, so constant lookup and so access, random access, and you can also like mutate it in place. And right, so this prim vector thing that has to do with something called the ST monad, which we haven't talked about, and I think there's also no lecture for that. But that's actually, I mean, maybe if we at some point we have time, we should probably talk about it briefly, because I think it's one of the coolest features of Haskell, actually. So the thing is, there is a way, it's called ST monad, which you can think of like a version of IO in which you can only, it's a little bit in that regard like STM, software transactional memory. So it's like a restricted version of IO in which you can only mutate, like for example, these vectors, these mutable vectors. So you can't write anything to the screen or do networking or so on. So all you can do is you can mutate mutable variables. But the cool thing is that so you can do this, but then there's an escape hatch back to pure code. So the idea is you, for example, have an array, then you run some algorithm on it that does lots of mutation of the array. But once you are done, you do something called freeze. So you basically from this point in time on forbid mutation, and then the whole thing is a pure function, so not in IO. So basically because it's still deterministic, so you do your thing, you mutate, but then in the end you have a deterministic result. And that is actually quite nice. So you don't pollute all your code with IO. It's still a pure function, but you do have this power of mutation. And as I said before, for some algorithms, that's actually necessary. For very few, but some. So yeah, Haskell has that. And that's why we get this weird um, type signature, because it doesn't only work for IO, it also works for this so-called ST monad, which has this feature that you can like turn it back into pure code. But anyway, that's also quite advanced, so we can just think of IO. And that's basically it that we wanted to say about vectors or arrays. And as I said, so arrays are similar. So for arrays, there are also all these versions. I mean, unboxed, boxed, and mutable. And they, as I said, I mean, they are older and more primitive, but I like them because they allow like arbitrary indices, not always starting at zero, and because they allow higher dimensional arrays as well. So sometimes they are, yeah, I also like them. But if you just need like one simple one-dimensional array, then these vectors are very nice. Okay, are there any questions to this?
Not so far.
Okay, so the next chapter is strings, which we have done on Thursday already. So string, text, byte string. Right. And now the next chapter would be binary serialization. So should we have a short break first? We have been going on for exactly an hour, basically.
Yes.
Okay, like 10 minutes or?
Sure. Yeah, 10 minutes. And if anyone has any questions, feel free to ask them right now. We answer it in 10 minutes.
Okay, I mute myself, but then somebody has to unmute me again, I think, because I can't unmute myself. So,
Okay. I think, Lars, if you enter with this separate link that I have, you can unmute yourself. I will share it with you.
I've unmuted him, so that's okay.
Thank you, Anderson.
Okay, I'm back, and I could indeed unmute myself now. Maybe wait for another minute or so before we continue. So should we continue?
I'm here.
Okay, right. Then let me share again. Right, so that was that. So we have just, I mean, seen like a glimpse of useful, very useful libraries in Haskell. If you want to do actual, I mean, get things done. I mean, the map and set types are really useful. I mentioned that last time already. The sequence type is very nice. And now we have looked at arrays or specifically vectors and mentioned that they come in different flavors like unboxed and mutable. So now we look at a different topic, serialization, binary serialization. I mean, non-binary serialization we have talked about before. So, I mean, serialization denotes the process of converting data into a format that can be written to disk or sent over a network connection. And deserialization is the opposite process. So reconstructing data from a file on disk or from something sent over the network. And I mean, one example are the show and read classes that can actually be used for this purpose. So if you have some arbitrary Haskell data type that has a show instance, you can use show to convert it to a string, and then you can, for example, save that string as a text file on disk. And with read, you can pass it back in. And so, but show and read are made for human consumption. So they are supposed to produce something human readable. They're not made for efficiency or a compact representation. And read is actually a form of parsing. Or so parsing is a form of deserialization. So getting some text, for example, and passing it back into a Haskell value. And of course, there are like several textual serialization formats. I mean, XML used to be very popular like 10 years ago or 15 years ago. Nowadays, I think JSON is more important. Then there's YAML. This is, I think, a bit more modern than CSV for a comma separated value for spreadsheet-like data or database tables and so on. And for all of those, there is support in Haskell. So, I mean, not built in, but there are libraries on Hackage that can deal with all these file formats. And maybe we'll look at some of them later. I think I mentioned ASON already, maybe, which is like the most commonly used one for JSON serialization and deserialization. But apart from these textual formats, there's also binary formats. And as we mentioned briefly on Thursday, Haskell has the byte string type for that. So which, as the name suggests, is just a string or stream of bytes. And then they can, of course, be much more compact than human readable formats. So if it's just about like compactly, efficiently storing data, then you would probably use a binary serialization format. And there are lots of them available as libraries as well in Hackage. Some of them are binary store serial, and we'll look at binary in this lecture. Actually, I think the Cardano node uses, I think, serial. I mean, because it uses this CBOR encoding, which is, even though it's binary, it's sort of, I mean, it's more structured. But nevertheless, so we look at binary, which is also, I think, one of the oldest. And I think I have imported that already. Is it data binary? Let's just see. Yes, I think so. Just reload. Right. Right, and there's a binary class. And in principle, it has these two main methods: binary t, put, t to put, and get t. And if we ask what this get and put is, so if we ask for put, you see this is just a synonym for put m unit. And if we ask for put m, probably it's not in scope. So let me just import that. So if we ask for information on put m, we see it's monad, in particular monad. And if we ask for information on get, then we see it's also monad. So we have these, the put m monad. So put without the m is just the abbreviation for put m unit, and get. So the idea is basically put serializes and get deserializes. But this is like low level stuff in the library itself. And then like if you, as a user of the library, there's this encode, decode, and decode or fail. So binary is the type class that says that type A is serializable. So with encode, you can serialize it into a byte string, and with decode, you can deserialize it from a byte string. But of course, that can fail if the data is not, I mean, if it doesn't correspond to something of type A. So there's also this decode or fail, which will not just crash if it's invalid data, but instead will either give you a left or right value depending on whether it failed or succeeded. So if it succeeded, it gives you the A. If it failed, it gives you the error message. And in both cases, it gives you the unconsumed input and how many bytes it read. So maybe we should first try to play with this a bit. So yeah, the code is in there. I should also probably import. So we see it, byte string here is lazy byte strings. We mentioned them last time. So let's also data byte string lazy byte string. So to make the types more readable. Okay. And decode or fail. Right, so let's try it out. I mean, if we ask again for information on binary, then we see lots of instances. So that are already provided out of the box. So in particular, I'm sure we'll see like primitive types somewhere. Okay, yeah, here. So character, for example, Booleans, floats, integers, and then I mean all the words and so on, and then also, for example, there's an instance for list I saw somewhere here. So if A is serializable, then so is lists of A's, and here we have the tuple instances. So if A and B are serializable, then also pairs of A's and B's are. So I don't know, let's take, for example, a pair of an Boolean and a string. So if we, for example, have pair true Haskell, so type is pair of Boolean string, where string is a list of characters. So this should be encodable. So we can do encode pair. Okay, well, so this is the encoding of this pair. So we, for example, call BS byte string. And now we can do decode BS, and we have to tell the compiler, same as for read, what pair we, what type we expect. And we get our value back out. Now we could try, I mean, if we try for some other pair type, I don't know, integer, then it crashes. And now we can do this decode or fail. The only problem is I have to give this type signature. So this is now either just 1 second. Let me just ask for the type again. Right. Let me import this data.binary.get as well. Okay. And now I can give my type annotation. So decode or fail BS. So if I use the right type, so either byte string, byte offset string, byte string, byte offset, pair of bool, comma, string, then as before it should succeed. So I get a write. So no bytes left, 16 bytes consumed, and this is the decoded value. If, however, now I give integer here, which should fail, it failed before when we used decode. So now I get a left value, no bytes left, 16 consumed, and error message, not enough bytes. Yeah, that's how you can use it. So for encoding and decoding, for serializing and deserializing a large variety of Haskell values. And okay, we saw this. And so I already showed you that put m and get are actually monads. So in particular, of course, because functor and applicative are superclasses of monad, both of them are also functor and applicative. But we see that get is also alternative in monad plus, which is exactly the type classes we had for our parser. And we saw that once you have that, you can basically, I mean, easily write parsers. So in the lecture on parsing, we saw once we have like monad plus and some very few primitives, you can basically do everything, parse every Haskell value. Right. And there are some primitives. So to put a byte, to get a byte, to fail with an error message. So let's try this. Put word 8, I don't know, like 42. Okay. Right. I mean, it's put, it doesn't have show, but we have this. I mean, I can ask for the type at least. Right. Okay, and then we have these file versions. So earlier the encode just results in a byte string, and the decode takes a byte string, but there are also file versions. So it gets a file path and then writes they encoded the serialized value to this file, and decode reads it from the file again. And also a version as before that basically fails or succeeds. So it's a bit different. It only has this offset, and so it doesn't have this the consumed bytes. And in the success case, it just gives the value. Right. So that's good. And now let's look at an example. If I mean, we saw a lot of like common types are already out of the box supported, but what if not? So let's look at again at this tree type that we have looked so often. So leaves of type A, nodes with 2 children recursively. Let's derive show. Okay, this is node, this is tree, of course, sorry. And now let's say we want to serialize trees. Maybe we should have an example tree. Example tree, tree string. Example tree, I don't know. Node, leaf, Haskell. Okay. Okay, for example, this. Right, and now let's say we work with these trees and we want to serialize them, for example, to disk. So we need a binary instance. So instance binary tree A. So first of all, I mean, at some point we have to serialize the leaves, and at the moment they are of an arbitrary type A, about which we don't know anything. In particular, we don't know whether it's serializable. So we obviously need as a constraint that A is serializable. Okay, and now we have to implement get and put. So put takes a tree A, gives us a put. Now I need this instance sick. Again, and get of type get tree A. Okay, how would we do that? First of all, I mean, nothing we learned in this course, I mean, is like superseded by other things. So, I mean, the very basic lectures about how to write functions operating on types are still true. So because tree has 2 constructors, we probably need, I mean, for our put, we need 2 equations. So one for leaf, one for node. So A. Right. And now, I mean, we also have to think about, I mean, if we deserialize it, we also have to deserialize it again. And I mean, one thing here is, I mean, we have these 2 cases. And so if we later want to deserialize again, we should know whether we are looking at a leaf or a node. So somehow we must indicate that when we serialize with a, so the idea is to give a tag or a marker, and we can just use 1 byte, a bit, yeah, byte. So we can use this put word 8. And this is now completely arbitrary. Let's say we use, I don't know, 0 for leaves and 1 for nodes. So I do this. And in the node case, I first write a 1 byte. Okay, and now how do I serialize the leaf? Well, all that's necessary to reconstruct the leaf is the payload of type A. And we have binary A as a constraint. So we know A is binary. So we can just not recursively, but use the binary instance of A to put A. I mean, the A is now of type A and A is serializable. Okay, and in the node case, also quite simple. We can just serialize first the left child and then the right child. So recursively, we do put L and put R. Right, and now for getting, I mean, there the strategy, obviously, we first have to read this tag. And then depending on whether that's 0 or 1, we know whether we have to pass a leaf or a node. So let's use a do block for this. So first, what was it called? Get, I think, get word 8 to get this tag. So word is get word 8. So now we're reading this first byte here. So if, yeah, 0. Yeah, okay, fine. So what do I do in this case when now I must just, I mean, I first read the payload. So A with get. And now I return pure leave A. But of course, we do this more compact using applicative notation like so. Okay, so now I have choices. I mean, if it's not 0, I can assume it's 1 and just do the node thing. Or I can also be more defensive and say, if it's not a 0 and not a 1, then I fail. So I don't know. Let's do this. So if W equals 1, then, okay, I'll deal with that in a second. But else I use fail, expected or unexpected tag or something. Right, so leaves the node case. So, but there I just have to read recursively get the left child, get the right child, and then combine it with node. So in applicative syntax, this is very nicely written like so. So that's the same as saying, first I get L, bind the result to L, I get again, bind the result to R, and then I purely do node LR. Okay, so that's that. Now we can actually try it. So we have our example tree. So I can do, what was the type? Encode file. So it takes a file path and an A. So for example, I can say encode file tree, I don't know, .bin for binary example tree. Now it should be here somewhere. Yeah, there. That's now okay. Binary file. Not sure I can. I actually don't know. Is there a good tool in Linux to look at binary data? Do you know what you know?
Maybe cat has a flag for binary data.
Okay, let's see.
No.
Dump or something? I'm not sure.
Mm.
Let me just check quickly. Sure, there's some standard tool. Linux display binary file. How to view binary file? Hex dump. Okay. The answer here, hex dump -c, your file. Okay, let's try this. So I do hex dump -c tree.bin. Okay.
Nice.
And we see, yeah. So we should see we have these markers and 0 was for leaf, 1 was for node. So we see first the whole thing is a node, so that's this 1 byte. Then it's again, if we look at the, so there, yes, then it's again a node with 2 leaves. So this is now of the left child. The left child is again a node. Then will be then it's a leaf. So this 0 is for the first leaf. Then this here is the payload. That's the Haskell string until here, I think. Then the second leaf, that's the Rust string. And now we have passed the left child. So now we have passed this until here. And now it's, I mean, maybe it would have been better. So let me do this again because zeros are so, I mean, it doesn't matter what I do here. I can just, whatever, do 10 and 11. I mean, it's just 1 byte. It's not less efficient. Just then it's, I think, easier to see.
Right.
Let me do this again. Yes. So now the 0b is the marker for nodes and the 0a is the marker for leaf. So we have node, node, leaf. That's this here, node, node, leaf. Then comes the payload, the Haskell. This is done here. Then the 0a is now the marker for this leaf here, for the Rust leaf. Then we until here. Now we are done with the left subtree. So we're done with this. So now the next marker is for this leaf here, 0a. And this is the C string. Okay, so now of course we also want to see whether we can pass it back. So decode file or fail. So decode file or fail. Tree.bin. IO either byte offset string tree string. And it succeeds and I get my tree back. And if I gave a wrong type here, whatever, I mean, then something goes wrong and I get an error message. Right, because it tries to read an int and then probably, I mean, when it tries to pass this here as an int, then it probably only has to read, I don't know, 8 bytes or something. So until here, and it reads, and then it encoders the 61, but there should be a marker, so it should be a 0a or 0b. So that's why we get this error message, unexpected marker. Right. So yeah, that's that. And I don't know whether we will have time in this course to talk about generic programming. Hopefully we will at some point. Because you not very rarely have to implement something like this by hand. So even though, I mean, we talked about these built-in type class, so there are these classes that are built into the Haskell standard, like show and read and eke and odd, which you can often automatically derive with this deriving clause. Then there are those that are not Haskell standard, but nevertheless are supported by GHC, like functor, foldable, functor and foldable, that you can also add to this deriving clause. But this is, of course, always like a limited number of classes because, I mean, it must be supported by the compiler directly. But there are several mechanisms in Haskell to make this like more generic for other classes as well or other situations. One of them is called generic programming. And I think binary uses that. So as I said, I don't want to go into that now, but the gist is that in practice, it's very rare that you have to do something like this encoding by hand. So this code will normally be generated for you. nevertheless, I think it's interesting to at least see it once how this works. I mean, how you would implement it by hand if you had to. Okay, let's see whether I forgot anything. So this is basically the same implementation that we had. So are there any questions to this serialization?
Not so far. We
And I
can
should
wait.
also mention, yeah, sorry.
We can wait a minute just in case.
I can just ramble on. I mean, even if you don't use binary, if you use one of the others, I mean, normally they are in spirit very similar. So, I mean, I mean, for example, as on the JSON serialization also uses a monad, I think, for get input. I mean, it's maybe not called get input, it may be called something else in various libraries. But the idea of these serialization libraries is often similar, that you have some sort of type class. In the case of the ASON library, it's called, there are actually two JSON and from JSON. So they split it into two parts, I mean, because, yeah, whatever. Like show and read. But they are also then normally you have to implement something that's in a monad normally. So it's, if you understand one of these, then I think it's easy to work with others as well normally.
No questions so far.
Okay, good. And yeah, as I said, normally you don't have to worry, and most types already out of the box supported, or it's easy to get support for your own types without having to write code. Okay, so the next topic is like now not Haskell specific per se. It's more crypto or blockchain specific. It's just an example of an interesting data structure that maybe those of you that have worked with blockchain before have heard of. I mean, especially in Ethereum, it's a very prominent data type. I think in Cardano, it's nowhere like built in, is it? I'm not sure. Maybe something is implemented
Wait,
as a Merkle tree.
no, but we have a library from the Hydra team to build.
Right.
Yeah.
But that's just a library, right? It's not built. I mean, I don't know very much about how Ethereum is implemented, but I believe they, like at the central point, use Merkle trees
Mm.
for their like everything basically. It's a big Merkle tree. But in Cardano, I think it's not as important, but I mean, you can implement it. You can also implement it in Plutus. So the Merkle tree, or also called hash tree, is a normally perfect binary tree. So perfect, as I said, where all the leaves are at the same level at the bottom. So it has a power of two number of leaves. I mean, 1 or 2 or 4 or 8 or 16 and so on. And each of those leaves has some data attached to it, whatever, but it must be serializable data. And you also look at the hash of the data. And then the hash of the intermediate nodes is a combination of the hashes of its children. And that goes all the way up to the root. So you have these, maybe you have heard the term Merkle root. So here's an example of a Merkle tree with four leaves. So that would be this L1, L2, L3, L4. And then the way it works is so whatever the data in these leaves is, it's serializable. So you can hash it. And we mentioned hashing very briefly in the very first lecture about blockchains. So that's how you can, I mean, there are many, many different hashing algorithms, but each of them takes a byte string of arbitrary length and converts it to a hash, which is again a byte string, but of a fixed length, for example, 32 bytes. So that's hashing. And the point is, if you recall, that basically different inputs should give different hashes, even though mathematically that's not possible because you have infinitely many potential inputs, but only finitely many outputs. But nevertheless, a good hashing function makes it look as if that's true. And it's very unpredictable, even if you only change one bit of an input, the hash should look completely different and unpredictable. So anyway, so we have our leaf data, then we hash that. So we have these four hashes. And now when we go up in the tree at such a node, we have like the hash of the left child and the hash of the right child. And then we combine those two hashes. So for example, I mean, these hashes are again byte strings. So we can like just concatenate them. So let's say this is a hash, has 32 bytes. So we concatenate this with that one. So we have 64 bytes. And then we hash the result. So we hash the concatenation and get again something with 32 bytes. Do the same on the right side. And then again, one level up. So now we have this hash and that hash. Again, we concatenate and hash the result. And we get this top hash. And that top hash is also called the Merkle root. And the cool thing, I mean, why would you bother? Why do you do that? So the cool thing about Merkle trees is I mean, if you just know this Merkle root, so just these 32 bytes, then I can prove to you that any of those 4 elements is actually in the tree. How that is done, we'll look at in a second. But it's a beautiful and very clever idea. So the idea is, I mean, if, for example, you are on a mobile phone, and I mean, this is a tiny example, of course, but this could also be like 81632 or whatever, 4096, or it could be millions of leaves. So this whole tree could be very big. I mean, could be gigabytes big in principle. But all you need to know is these 32 bytes at the top, and then somebody can prove to you that a given leaf is indeed in the tree. And so you don't need any of these gigabytes of data. And the proof is quite short. And so yeah, that's so-called, I think it's called verified data structure or verifiable data structure. So I mean, it's one, for example, use case is that there's a mobile client that doesn't have much memory. So the mobile client basically only has to store this hash, and then nevertheless can basically be sure that the person that actually stores the tree doesn't lie to him about the data in the tree. And the idea is very clever how this works. So if I want to prove, so this is now another example with 8 leaves. So if I want to prove that this element is actually in this Merkle tree. So what I use as proof is, so I give this element, and then each step up the tree, I mean here, for example, so I have this element, so now I have to go up one level. So then I basically in my proof include this hash. So always the hash of the path I didn't come from. So here I come from the left, so I include the hash on the right. Then here I come on the right, so I will include the hash on the left. Finally, I come from the left, so I will include the hash on the right. So this so-called Merkle proof will have this hash, and that hash, and the actual value. And the point is that with just these 3 hashes, one can now reconstruct the Merkle root. I mean, I have my value in hash it. So I have this hash. This hash is part of the proof. So I have both of them. So I can concatenate them and compute this hash. Now this hash here is part of the proof. So I can concatenate these two and get that hash. This hash is part of the proof. So I can concatenate those two and hash and finally get this one. And this I can then compare with the Merkle root I know. And if I get the right value, then I know it's true. I mean, modulo, I mean, of course, it's not like mathematically true. It's true as long we can trust hash algorithms that they are good and unpredictable and so on. And the point is, I mean, here in this example, maybe it's not very convincing because the tree is still relatively small. It's just so the proof is still, I mean, the value and these 3 hashes. But the point is that each time I add one level to my tree, I double the amount of data in it, but my Merkle proofs only become 1 longer. I mean, that's the beauty of trees. That's also the reason why maps and sets in Haskell are so efficient, because you basically, I mean, in the case of binary trees, you double the amount of data by only adding 1 to the path length from the root to the leaf. So by only making the Merkle proofs 1 hash longer, I can cover twice as much data. So these Merkle proofs are relatively short. They are only logarithmic in the number of leaves in the tree. But yeah, but then I can prove to somebody that, I mean, as long as I know the root of the tree, then nobody can lie to me about the data contained in it. So, I mean, that's a common way to, or one possible way to put like things on the blockchain. Because in principle, you only need to store the hash, the Merkle root in the blockchain. And so I think it's beautiful. And I also think it's better to actually see that in action. I do have that ready made, but I think it's more fun to do it from scratch, maybe. Or what do you think, Robertino?
Yeah, I think it will be cool.
Yes. So let's let's hope I can do this. Let me just, so I have it here, but just you just call it Merkle tree just because I already have Merkle. Right, and I think that will also be like a recap of some of the things we have done. So let me just tree module tree. Okay, right, and let me reload because I changed the Cabal file. And I mean, with things like this, it's always good to, I mean, there are like 2 ways to do programming. I mean, to develop something top down and bottom up. I'm not sure whether one is better, but I would say that in functional programming, we tend to do it bottom up, which means you basically start by building little helper functions and little tools, and then combine them, these little functions to bigger functions until eventually you have your big thing.
Lars, we have a question slash misconception.
Yes.
Yes, so this is the question. So in practice, a Merkle tree, a Merkle leaf will represent a machine or miner in the blockchain?
No, I mean, it could, but I think, I mean, it's arbitrary data, whatever you want to have there. So whenever you have a use case where you want something, actually, I'm not completely sure what they use it for in Ethereum, but not for machines or miners. I think it's more like data and storage, probably, or like account balances and so on.
Yeah, I mean, it would make sense of the actual history of the blockchain.
No, I think nothing like that. I'm not sure. I mean, we could try to find out. Merkle tree Ethereum. Yeah, authenticated data structure. That's the word I was looking for. So that's the term for something like this. I have no idea whether that's now enlightening.
I mean, I think we are going to use it for Mithril or something like it.
Yes.
Maybe, yeah.
Yeah, I mean, they have this. This is basically the same picture. So you're happy. I think they store.
No, but that's just transactions, regular transactions.
Yes. Yeah, I don't know what they use it for, but not miners or machines. maybe one should read this.
No, maybe what are you going to use? I mean, we could give more examples, like if you want to have a contract and you want to make sure that the contract is signed by both parties, but it's never changed after that. So you could use like a Merkle tree in
For
which,
the signatures, or
yes, for the signatures and maybe for the each party's responsibility.
right. I mean, it's normally, I mean, you want to prove that certain things are, I mean, I think, I'm not sure. I mean, you could, for example, like all the blocks, I mean, in a blockchain principle, I mean, you could, uh, so you could prove that yeah, for example, if you want to prove that a certain block is in the block, I mean, that would be one possibility. I'm not sure whether Ethereum or anybody uses it like that. But I mean, you could have a Merkle tree where the leaves are basically the blocks in principle. And I mean, maybe not until the newest, but like until an hour in the past or something. And I mean, that's a huge amount of data. That's, I mean, for something like Cardano, it would be more than 100 gigabytes by now, I think.
Mm-hmm. Yeah.
And so in principle, you could do that. So you have a Merkle tree of all the blocks in the blockchain. And then, I mean, at least for one snapshot of the blockchain. I mean, it changes all the time, of course. But let's say you have, I mean, now for the history, you build a Merkle tree of all the blocks in the blockchain, and then you have this Merkle root. And as long as you trust the Merkle root, I mean, if that's like, I mean, if enough people agree on that, then you yourself don't have, I mean, okay, fine. I think that's actually a good example, even though it's maybe not what's done in practice. So let's say I have all the blocks in my blockchain, um, and I'm on a mobile phone, and I do know the Merkle root. So there's one hash, 32 bits, so very tiny amount of data. And now I use some service, some third-party provider, and I want to like look up a node. Maybe I want to write a blockchain explorer or something. So I want to look up one of the thousands or millions of nodes. And then I ask this provider, and he gives me a node. He says, okay, the node, whatever, 3775 was this one. And now normally I mean, I have no way of knowing. I mean, if I don't download the whole blockchain myself, I can't be sure that that's actually, that he is not lying to me. But with this Merkle tree idea, I mean, if he gives a Merkle proof together with the node, then I can just check whether with this Merkle proof, I get the right Merkle root, and then I can trust him. I mean, provided that the Merkle root is correct. And I think that's basically in a nutshell also how Mithril works, right? Or something like that. I mean, similar to that, I assume.
Yes, we drop the metadata, but other than that, I think it works like that.
Yes, so it's basically, so you can be on your mobile phone, you don't need any data except for this Merkle root. You don't have to trust anybody. So somebody, I mean, of course, people can refuse to tell you, but they can't lie to you. So if somebody gives you a block, and then you can, I mean, use this Merkle proof to convince yourself that that is actually right. And that exactly that block is at exactly that position in the blockchain. So yeah, that's a way to do stuff like that, that you have lightweight clients that don't need the full history of the blockchain in order to still like I mean, don't need trust. You don't need to trust anybody, and nevertheless don't need all the data. Yes, I think that's basically, I mean, of course there are like variations on this theme and so on, but and I don't know exactly what they do. I mean, they have these snapshots. I mean, whether every day or so they do this new, but in principle, that's the idea.
Yeah, but the snapshots are part of the consensus
Mhm.
mechanism, so it's
Yes,
not about verifiability.
right. I mean, what I mean is this Merkle tree is a it's a static thing. You can't I mean, you can't add nodes to it afterwards. I mean, not to this simple data structure. I mean, there are ways to do that as well, but I mean, Merkle tree is a static thing, so it would just be like a fixed amount of history of the blockchain. So
Yeah.
so you have to do something extra if you want to like keep it dynamic so that it updates to newer versions. but yeah, anyway, that's, I mean, that would be one use case. Or I mean, anything really where you have like numbered or indexed things that you can't all hold in memory, so you want to use a third party to look them up, but you don't trust that third party. I mean, you could do the same for, I don't know, anything that's, I can't think of good examples except blockchain. Anything that is like indeed index from zero, I mean, with a number. Yeah. Right.
Okay.
Okay,
Says
well,
that clears this up. Thank you.
welcome. Okay, so as I was rambling about bottom up and top down, so I mean, in order for all of this to implement that, first we need to, I mean, know how to hash something. And I mean, as I said, hashing works on byte strings, but we don't want to restrict ourselves to byte strings. We would like to use arbitrary data in our Merkle trees. So we have like two problems. One is to convert arbitrary data into byte string, and the second is to hash a byte string. So the first problem we just talked about, that's topic of binary serialization, which we have solved basically. So let me just import data binary again. And I think I only need binary and this encode function. Okay, and the second question is, how do we hash? And I mean, in general, it's anyway a very bad idea to try to do that yourself, because there are lots of things you can get wrong and then it becomes insecure. So I will use the Kryptonite language, library on Hackage, even though Robertino told me that maybe this is no longer supported, but I think for the course it's good enough anyway. I know Cardano was using that like excessively everywhere. Not sure whether we changed. So this is just a package on Hackage called Kryptonite, which basically has everything you ever dreamed of concerning cryptography. So it has all these ciphers and public key encryption and also hashing. So
There
yeah,
was a problem with the maintainer, but I think like it's still somewhat maintained by someone else or something like that. So,
right. This Vincent, he actually used to work for IRHK, and he's also like doing Rust, but he worked for us. I'm not sure whether I think he left. Not sure. Okay, and here's this crypto hash, and then we have crypto hash. Sorry. So, oh yeah, and this is also maybe a nice exercise now, a nice demo about how to navigate libraries. So the goal is I have a byte string, a lazy byte string. Speaking of lazy byte strings, I should import data.bytestring.lazy byte string. Right. And what I want is I want I want a type of hashes, and later for this operation, so if we go back to the slides, we always have to like take a hash from the left, take a hash from the right, concatenate them as byte strings, and then hash again. So we need something hash to byte string. I mean, a hash is basically a byte string, just one of a fixed length. So we need something of type hash to byte string. And finally, we want to hash arbitrary stuff. I mean, arbitrary serializable stuff. So we want a function hash that if a type is binary, given A gives us a hash. So that's what we want. And now we must see, I mean, if I tell you now the Kryptonite library is good for this, we must see what we can get from that. And that's often I mean, if you ever do Haskell like professionally or also as a hobby, you will often find yourself in this situation that you I mean, you find some library, you Google whatever you want, you need, find some library, but then of course, normally it won't have exactly the stuff you need. So you always need to first understand how the library works, and then also normally write some sort of converter functions to like shape it into the form you actually need. So I mean, if I now didn't know this, and actually it's been a year or so since I last looked at that, so I can simulate this. So this crypto hash looks promising, right? And there's also an example. I mean, that's okay. This uses SHA-1, and there seems to be something called hash. So this looks promising. And I mean, I don't know. I think Cardano uses SHA-256. So maybe we should use that as well. So first of all, so it seems it supports lots of different algorithms. And if we look here, it's a long list of hashing algorithms. So MD5, for example, is I think used for like fingerprints of files and so on, but I think that's insecure. So here's this SHA-256. So maybe you should stick with this.
Yes, and in next update we add Blake too. That is also somewhere there.
I saw that somewhere, yeah.
Yeah,
Yeah,
but
there. Right. So let's, for example, use SHA-256. I mean, it doesn't matter. You can do Merkle trees with everything. We could even parameterize our Merkle trees over the hash algorithm, but that's maybe getting a bit, going a bit far. So, right. So maybe, so I mean, in this example here, they use crypto hash. So maybe I should start with that. But I think I imported qualified. So to not get confused, let's call it, I don't know, crypto. Yeah, and now of course one should never do this because everything should always compile at each point. Let me just, for the time being, to make it compile, I just make hash a synonym of byte string, which is maybe also not even a bad idea, but nevertheless. Yeah, it's always good to have everything compiled, even if there are gaps, because right, because then, for example, you can use the REPL. Okay, so now I mean, there was this example where in the example this hash function was used. So let's see. So it has some very intimidating constraint. Then it has this hash algorithm A, and it takes some BA, whatever that is. I mean, that's this byte array access, blah, and results in a crypto digest A. So we want, and if we want to use SHA-256, so I think so that's not in scope. I need these algorithms as well. So let's import this as well. Sorry, my editor is acting up again. Why? Why? Yeah, I have caps lock in. That's always bad. Right. Okay, let's crypto SHA-256. Okay. So we see this, whatever that this does. Sorry, where was I? Here. So I mean, the result of this hashing function is this thing called digest. So I mean, one idea would be to define our type hash as that crypto digest, and now for this A, we wanted to pick crypto SHA-256. Okay. Right. So now I mean, this BA thing, what's that? And I can try to import that as well. So it's in this memory package. data byte array. Let's see whether it gets less intimidating. Sorry, no hash. Yeah. Right. Okay. This byte array access, whatever that is. So let's ask. I mean, I did in my Cabal file. So I included this kryptonite, and in my wisdom, I also already included this memory, which is where this byte array access thing lives. So let's ask about this. And we see do we see anything? So it's all a bit intimidating. I mean, somehow we want to. I mean, what is bytes? I have no idea. Context. Let me just so in cases like that, one would probably byte array access package. Try to look at documentation. So there's this class. And this is good. So it seems there's an instance for byte string. And there it's always not clear because byte string there is lazy and strict. So it seems to be strict. But we have, I mean, our serialization gives us lazy byte strings. So there's one problem, but I mean, this is already good. So we have like strict byte strings that we can use. So again, I mean, why am I looking at this? Because the type of hash or crypto, not hash, crypto hash, is it takes a BA, which must be an instance of byte array access. And one option seems to be byte string, which is good. So in order to I mean, first of all, we have our A, we want to hash it. So first thing we can do is,
Lars,
yes,
before we moving on,
yes,
AM ask, not sure if I understand line 9, the type synonym. Is hash aliasing two different types?
no, it's like maybe. I mean, digest takes a parameter.
Right.
So
Okay.
digest,
If
digest,
if we show the type of digest, there we go, there we go. Yeah. Because I think previously it was like without importing, so it looked weird.
yes. I mean, crypto digest takes a type parameter A. And that type parameter must be one of these hashing algorithms.
Okay, it says that it got it. Thank you.
Right. Okay, so as return type, that's fine. We can use this, but now as I mean, what we put in, it must be something that is an instance of byte array access. And we just looked in the documentation that byte string seems to be that. I mean, which makes sense because hashing should go from like bytes to a hash. Okay, so now, but we have an A, but we learned about serialization before, so and that's why I said A must be an instance of binary, so we can encode A and then like try to hash, so crypto.hash. But this probably won't work, right? Because it says can't deduce byte array access byte string. And I think, I mean, we do see it here that it should, but I think the issue is that this is a strict byte string. I mean, if we click on it, we see we are in data.bytestring and not in data.bytestring.lazy. So we have this, where's the encode gives us a lazy byte string, but for hash, we need a strict byte string. So, but no worries. So we can, I mean, I mentioned that at the end of last lecture when we talked about lazy byte strings, that you can convert between the two. So there is something lazy byte string from strict and to strict, I think. So we need to strict. Why did it do this?
It was because of the dot lazy.
Yeah. Okay, now this seems to compile. And we don't even need this byte array stuff. Maybe I think we do need it later. But anyway, so right, so this is this. So now we at least have something that we can try. So let's try it. So something that's serializable, and we know a lot is. So for example, true and I mean pairs of booleans and whatever string is serializable. Okay. And okay, so we see if we make a small change, like the hash is completely different. So this is good. So that looks promising. And I just wanted to demonstrate that, like, because that's problems I have all the time. I mean, you always have to juggle with like encodings and lazy byte strings, strict byte strings. And that's just one of those things one has to endure. And I mean, look in the documentation, see what it does, and then, I mean, be aware that there are lots of conversion functions and so on. And of course, I mean, one can write it like this, but of course, as functional programmers, we prefer to write it point free like this. But that's just a matter of taste. Right. So now we have this hash. Now, what about the remaining thing is this. So how can we get from this digest type to byte string? I mean, it looks like a byte string. So, and this is now where we can, so, I mean, digest, what's digest? Let's see what it can do or what it is. Right. So we see that digest all, I mean, we would like some way to, I mean, there's digest from byte string. Okay, fine. But as far as I know, there is no digest to byte string here anywhere in this. I mean, of course, that would be the first idea, but I think there is none. So what can we do? I mean, we don't even know what data is. Eq doesn't help. Read doesn't help. Show, I mean, I suppose we could like show it and then, I mean, it obviously hex or base 16 encoded, so we could use the show instance to get to this string. I mean, you could try this. Try to show. Then we have this string, and then we could pass that as base 16. I also mentioned that in the last lecture that for all these like different bases, there are libraries on Hackage and could get a byte string that way. But that's I mean, and in the worst case, we could actually do this, but it's obviously not the way that's intended. I mean, there must be an easier way. So the only, I mean, NF data we haven't talked about, but I can tell you that's not useful in this context. So the only like promising instance, I mean, first, of course, you look for like, or actually there is also a hash lazy. So maybe I wouldn't have needed this. Let me see. So maybe I don't even need this too strict and I can just use hash lazy. Okay. Right. That makes stuff already easier. So yeah, I mean, first one should read the documentation. So I, for example, didn't, and therefore I didn't realize that there's also hash lazy. So we don't need I mean, to explicitly convert from strict byte string to lazy byte string because there's a version that takes a lazy byte string. Fine. So that's good. But nevertheless, now we have this digest and we want to turn that into a byte string. And right. And the only, and of course, first thing is you read documentation and there is indeed a digest from byte string, but there's not a digest to byte string. And in cases like that, I mean, beginners are often flummoxed and don't know what to do. But often what you need is like hidden in one of these instances. And as I said, I mean, all of those are not very promising. So the only one that could possibly help us is this one. Right. So let's see whether there's anything useful. Uh, and I think there is. I just must find it. Right. There's this unpack. So you can, anything that has this weird type class instance, you can unpack it into a list of bytes, which sounds like close to what we want. I mean, we actually want a byte string. Let me see, lazy, actually we want a lazy byte string. I mean, that's also, of course, we could also decide to use like strict byte strings. Let me just see, where is this? That's data byte string. Actually, we want, sorry, data, nah, sorry. It's easier to go there. And then data dot byte string lazy. And there we see there's pack and unpack to convert between lists of bytes to byte string and from byte string to list of bytes. So putting this together, so from byte array, we have this unpack to get from our digest to a list of bytes. And then in data byte string lazy, we can use pack to go from list of bytes to a byte string. So I think that's the best way to do this. So, which means we can do this as, so first we use, and let me do this qualified as well. Let's call it whatever, BA for byte array. So I first use byte array unpack to get it into a list of bytes, and then I use lazy byte string pack to turn it into a lazy byte string. And I mean, this is also one of these cases where I prefer to use qualified imports because, I mean, as you see, all these names clash. I mean, you have unpack and pack in all sorts of different ones. So I find it much clearer if in this case you qualify it. So let's see. So so this was our hash, and now we have our hash to byte string. Right. Okay. Only and one thing I forgot. I mean, if you look back at the slides, another operation we need is to actually concatenate two byte strings to another one. I think there's also something. So we again that I mean would be good to look in documentation. So let's see, append. So there's something called append that appends to byte strings together, like concatenates them. So maybe we should also like define this here. So byte string, byte string, byte string. Actually, I don't know. I just feel playful and want to give it a name. So we can just use lazy byte string append for that. Okay, and then we see we don't need this. Okay, and that is like the basic stuff that we don't want to worry about when we, I mean, that's the low level stuff to actually do the work, the hashing and so on. So now we have like a mini library of working with hashes. So we can hash arbitrary stuff. We can convert the hashes back to byte strings, and we can concatenate byte strings. And that should now in principle allow us to do all these operations. Okay, so I don't know. It's again been an hour, so maybe we should have another short break and then do the Merkle trees afterwards.
Sure. Yep.
Okay, again, 10 minutes again.
Okay. 10 minutes.
Okay, talk to you soon.
Yep.
Thank you. Okay, I'm back. Should we continue?
I'm back as well.
Okay. Right, let me share again. One thing I should mention still, I mean, one disadvantage of this whole thing is that it has to be a perfect tree. So you always need a power of 2 leaves. And there are ways to fix that. And there the idea is that you can also have nodes with just one child. And then when you go up, you instead of, I mean, then you have nothing to concatenate the hash with. So you just concatenate the hash with itself and hash the result. And I think in my original example, I had a version like that, which is more realistic, but maybe it's not necessary. It's an unnecessary complication. So maybe we don't do that, or if we want to, we can do it at the end.
Maybe we can do it without and then show the code, the other code, so they can see the difference, and that's it.
Yes, although I'm not completely sure that's correct, my old code. But yeah, we can do that. Right, so let's first try this. Right, so first we need a type for our tree. And let me start simple. I will refine that a little bit later. So yeah, let's call it Merkle tree. Payload A. Okay, and it's quite similar to what we had before. So we have leaves, and the leaves have an A, but now we also need this hash. So the leaf should also have a hash, the hash of that A. Or nodes. So again, as before, we have 2 children, again, Merkle trees. But now again, we need this hash, which is the concatenation of the hashes of the 2. So I think sure. And one thing is so I mean, we always have to be sure that we calculate the hash correctly. And one trick that I briefly mentioned in the last lecture is these so-called smart constructors that can do things like that automatically for us. So I think this is a good way to a good example where they might be useful. So let's define smart constructors. So a leaf where I just give the A and get a Merkle tree and take care of the hash construction in this smart constructor. So, I mean, leaf A is supposed to be just leaf hash A. We now have our hash and A, but of course that won't work because hash complains it must be binary, which is true. So let's add this constraint. So now I can reload it already, so we can try it out, for example, with strings, leaf Haskell. So it's now leaf and the payload, the Haskell, but also the hash of Haskell. Okay, and let's do the same for node. So again, no, we don't. I think in this case, we don't need the binary constraint. So given 2 Merkle trees, combine them to a Merkle tree. Right, but now somehow I must combine the hashes of the 2 children. I must concatenate them. And how do I get them? I mean, that depends on whether it's a node or leaf. But actually, that's also silly, so I should have a helper function for that, which given a Merkle tree gives me the hash. So if I have my leaf with hash and payload, it's the H. And if I have my node with hash and 2 children, it's the hash. Okay, and using this, so node left, right. Okay, it's a node. The children are just this, but what's the hash? So I must hash. What do I have to hash? Well, I use my helper function to get the hash of the left child, and now use my operator to concat it with the hash of the right child. And why is this complaining? Because this is hashes, but I need byte string, so I also need my helper function hash to byte string of the left hash and hash to byte string of the right child. Right. So now I could do things like, so I have my leaf Haskell. Now I could do something like node leaf Haskell leaf Java. I reload. Right. So now I have a node. This is, and each of the two leaves has its own hash. And then so this will now be the concatenation. I mean, converting this to a byte string, that to a byte string, concatenate them and hashing again. Okay, so that's that. So now I can construct trees by hand, but of course I mean, that's tedious if I want to do this by hand. And also I must be careful about this perfect stuff. So let's write a function construct. So given a list of A's, which gives me a Merkle tree. I could also do maybe Merkle tree. Let's do it like this now. And the idea is, I mean, how do I do this? So I have like a list of stuff. For example, I mean, my leaves. Leaf 1, leaf 2, leaf 3, leaf 4, leaf 5, 6, 7, 8. And they are in a list. So what I want to do basically in each step, I always combine two pairs of, pairs of the leaves of the trees I already have. So now I would combine N1 and N2 to a node, L3 and L4 to a node, 5 and L6 to a node, L7 and L8 to a node. And then I would continue. So the idea is, so first I convert the leaves or the payloads I have into leaves. So I have a list of Merkle trees. And then I take this list and always combine twos, twos, twos. And then I do it again and again and again until I'm only left with one. So this was wrong, of course. This in the middle is wrong. So right. So I need a helper function which takes a list of Merkle trees, gives me a Merkle tree. Right, and how do I call this? So construct. So the idea is to first convert all the A's into leaves and then use this helper function. So how do I convert a list to leaves? Well, I can map my leaf function that we just defined over the list of trees and then apply this go. Okay, and I can eta reduce if I like to make it more confusing, but shorter. Right, so I need to write this helper function. Given a list of Merkle trees, always combine pairs of two of them until I'm at the root. So I mean, first case is I have the empty list, in which case something went wrong. Maybe because the original list was empty. I mean, I could try to make that nicer by insisting on non-empty list, but let's keep it simple for now. So in this case, I say error, I don't know, empty list of data or something. Okay, if I have exactly one tree, then I'm done. that's my result. That's my whole tree. Okay, and if I have oh, sorry, no, sorry. Actually, this should be, just think briefly. That's wrong, because then, I mean, when I reach the end, it would immediately stop. No, actually, what I want is, no, this is fine. Sorry, forgive me. I need like a go and a go prime. I mean, this is probably fine. Hang on. I need to go prime, which takes a list of Merkle trees to a list of Merkle trees. So this is the step. Maybe I call that step. List of Merkle tree. And now, okay, fine. And once, so sorry about this. Let me do this again. So I get my list, and now I call step on it. And so the idea of this step is it does this going down up. So I have my list of trees, and in each step I go through the list from left to right and always combine two to a new one. So I combine L1, L2 to this end, L3, L4 to that end, L5, L6 to this end, L7 and 8 to that end. So I get a new list of trees. So I started with 8 leaves. Now I have 4 nodes. Now I apply step again. I combine this end and this end to that end, this end and this end to that end. Now I have 2 trees left. I do step again, and I'm left with just 1 tree. And that's then my result. So in this go, I do the step, and now there are several cases. So if it's the empty list, then it's an error, no data or something. If it's just 1 tree, I'm done. That's my result. And if it's more than 1, I just recursively, sorry, I want to call step again, but I should give it a name. So otherwise I have to compute step twice. So let's say let twice step axis in case wise of so in this case I recurse with this shorter list, which now has at least 2 trees left. So then I will again call step and so on. So now for step, that's this where I have to combine packages of 2. Right. And now in step, so if it's the empty list, I'm done with this step. Now, if it's exactly 1 element, this is an error. This is if I don't have like the power of 2. So if for example, L8 was missing, I'm now in this step, I combine L1, L2, L3, L4, L5, L6, and now I only see L7. There is nothing to pair it with. That means something went wrong there. So number of payloads is not a power of 2. Right. And in the good case, so I have 2 elements and some rest. So in that case, I can use my smart node constructor to combine X and Y. And I concatenate that with recursively calling step on the tail. It's a Merkle tree. And why is this not working? Plus plus is wrong, of course. It's the first element of the list. Okay. Right. Actually, maybe to make it clearer, I mean, I can change it again later, but just like so that we can try it out. Why is this not happening? Binary. A. Okay, so let's just I now moved a step to top level so that we can actually try it. So let's but we need leaves to do this. So let's just define some. So L1 is leaf Haskell, L2 is leaf Java, L3 is leaf C, L4 is leaf Python. Right. So now I can, for example, do a step. So if I do step on just one leaf, for example, it will tell me number of payloads, not the power of 2, which is like the wrong error message, but yeah, so that's a case I didn't consider. I must consider that in Go already, I think. So if I'm only because I mean 1 obviously is power of. So let me just think. So this is wrong. I mean, it's actually true. I mean, for the step, I should never call step in this case. So I think where must here in this Go, I must have a case for this. So if my list of Merkle trees is, yeah, right. If my list of Merkle trees is exactly 1 element, then I'm done, and that's my result. Right. But I did that. Yeah, I did that. But I do it. Sorry, I'm a bit confused. I have to do that first, I think. So this was wrong. Let me rethink this. So if I have the empty list, it's error no data. If it's exactly 1, I'm done. And if it's more than 1, I want to do this step to reduce it. So I can just do go step XS. So this I can all. Right. I think this is better. I mean, I will still get the wrong error message, but I think the code is right now. So in this case, the step just fails. Yes, so the error message is wrong, but hopefully we'll get the error message, the correct one, like in the whole thing. But I mean, I can't combine an odd number of trees. But if I have L1, L2, it combines those to this node. If I have L1, L2, L3, it should fail again because it's an odd number. But if I have L1, L2, L4, then it returns me a list of 2 nodes. So it has combined L1 and L2 in the first node and L1, L3 and L4 in the second node. So now I can call step again on this. And now it's a list with 1 node. So this should be fine. So I think I make that local again. And now we should also get the right error messages. So if I now use this construct on Haskell, for example, just on 1 element, why now construct? Right. So this works. If I have Haskell and Scala, that works. If I have 3 elements, it should fail. Yes, and gives me the right error message, not a power of 2. But if I have 4, it should work again. Okay. So this is promising. Now, of course, we can at least construct these trees. Now, of course, the fun part is constructing Merkle proofs and checking them. So first, the construction part. So we need something like, I don't know, create Merkle proof. And of course, the question is, what is a Merkle proof? And as I said, it's basically for each node, I mean, for example, L4, let's say. So in order to get from the root to L4, I have to go left, right, right. So for each turn I take, I need the other hash. So I would need, since I go left here, I need this hash. Then I go right here, I need that hash. And then I go right again, and I need this hash. So it sounds like I mean, a proof is basically a list of hashes plus the final result. But in addition to that, it's not enough to have these hashes. I must also know whether I went left or right. Because then it depends in which order I concatenate them when I check the proof. So basically at each step, I must know whether it's left or right, and I need a hash. So one possible type to represent that, I mean, I could use a Boolean. I could pair a Boolean with the hash. That would be one option. Or I can use either hash, so a left hash or a right hash. I think it doesn't really matter. Must just decide on something. So Merkle proof A. So it's first of all the element itself, whose existence in the tree I want to prove. And secondly, although this is also not really necessary, because I can deduce, I mean, whether I go left or right, actually I can, there are always choices. I mean, if I know the index of my A, then I can deduce that, because the index follows, I mean, not sure what's better, but maybe it's more explicit if I make it explicit in the path. So let's say either hash and a list of those. And actually, maybe I should write it the other way around, because it's basically first these hashes until I reach my element, and then it's the element. But of course, it doesn't matter. Logically, that makes no difference. Okay. And now, I mean, how do we actually construct this thing? So given a tree, a Merkle tree, and an index, we want to construct this Merkle proof. So tree index. Okay, so let's start again with the leaf case. So in the leaf case, we don't care about the hash, we only care about the payload. What about the index? I mean, we should care about it because, I mean, it should be 0. Each other index would be out of bound. So actually, we should have a case for, sorry, index. So if our tree only consists of one leaf, which means we only have one piece of data in it, and which means the only valid index is 0. So if I is indeed 0, we can we get a valid proof. So we can return Merkle proof, the empty list. There were no nodes, so no like left turning left or right. We were immediately there, and our result. So that's this case. And otherwise, we have an error index out of bounds. Okay, so that's the leaf case. Now the interesting one, is the node case. So we have a node with a hash and left child, right child, and an index. Okay, and now we have a problem. I mean, obviously we want to turn left or right depending on the index, but we don't know where to turn because we don't know how many elements are in our tree. I mean, if we knew there are 8, then we know if the index is between 0 and 3, we have to turn left here. And if the index is between 4 and 7, we have to turn right. But we don't know that there are, I mean, if we just given this node, we don't know how many elements are in the tree. And that's why I said in the beginning, I will like change that slightly. So I think the best way to fix this is to also with each node remember either the height of the tree or the number of elements in the tree. I don't know, it doesn't matter. Let's say the number of elements. So we should, in addition to the hash, we should also like remember how many elements are in the tree. Right. And the nice thing is because of our smart constructors, I don't have to change much code. For example, I won't have to touch this construct function. So I have to change the tree hash because now here then there's this additional argument, the number of elements in the tree. I can leave the leave constructor alone, and I just have to like put the right number here. And what is that number? Of course, it's the number of elements in the left child plus the number of elements in the right child. So I could look them up, but then I have to do a case distinction again between leaf and node. So same as I did for hash, I should have a helper function here. Let's say tree count or whatever. So Merkle tree a to int. So tree count, if it's a leaf, it's 1 element. And if it's a node, then I don't have to do much. I mean, because I cache the number of elements there. I mean, alternatively, of course, I could just count, but that would be horribly inefficient. I mean, it's a big tree and each time I have to count. So that's why it's better to remember this element. Okay, so now with this helper function, I know what to write here. It's tree count left child plus tree count right child. Now I got some annoying. Right. So that fixes this. Let's format it nicer. Right, and as I said, the good thing, because I use these smart constructors, so the signature of those has not changed. I just needed to do more work in there. But that means because in construct, I didn't use the constructors directly, I used the smart constructors. I don't have to change any code there. So that's nice. Okay, and now, of course, I have this extra argument here. Okay, and now it depends whether I go left or right. Depends on the number of elements in the tree and my index. So, I mean, we know this number is always a power of 2. So I said I could have, instead of the power of 2, I could have saved this exponent. But I think this is also fine. So that means if our index, so let's see, I mean, here, for example, n is 8. So here, n would be 8. There are 8 elements in the tree. So now if my I is less than half, I mean, the half of 8 is 4. So that means if my index is less than 4, I must go left. And if it's greater or equal than 4, I must go right. So I can do this. So if it's less than dividing n by 2, I must go left. And otherwise, I go right. Okay. So what does it mean to go left for my proof? I mean, first of all, I can recursively call this create Merkle proof on the left subtree. So let's do this. So I have Merkle proof some list of hashes and my eventual payload. So this is by recursively calling create Merkle proof on the left, Merkle proof, yeah, on the left child with this index I. And now what? I mean, how do I get the final? What's the final result? Well, the A is the A that I found by recursively looking here. But now in order to turn a proof for this subtree here into a proof for the whole thing, I have to add this hash to my proof. So, okay, we worry about this now. So the payload is the same. So now what's this? So I have to add this hash. And now, I mean, this is now, I mean, I use this either encoding for left or right. So now it's debatable whether we should use left or right. I mean, we went left, but the hash comes from the right. So I don't know what's more natural now, whether for this case we use left or right. I don't know. It's really like a matter of taste, I think. I mean, it would read right hash. So maybe because the hash comes from the right subtree, we use the right constructor now. So right, and now what? So we want this hash, which is the hash of the right subtree, and we have our helper function tree hash for that. So tree, sorry. Ugh. As right tree hash of the right subtree. And then the rest of the proof is what we recursively looked up by descending in the left subtree. Okay, so that's the left case. If we have to go left, and now otherwise we go right. And let's just format this. Okay. So now, I mean, same idea. We recurse into the right subtree and add the hash of this node. So let's do exactly the same. Basically, so we go into the right subtree now, but now the index, we have to change the index. When we went left, we could leave the index alone. So, I mean, in our example, let's say we wanted to look up index 2, for example. So 2 is less than 4. So at the top, we have to go left. But in this subtree, I mean, it's still index 2 because it starts counting from the left. However, if, for example, we want to look up index 6, which would be this L7, we have to go right. But now in this subtree, which used to be index 7, maybe I should write the indices below this, 0, 1, 2, 3, 4, 5, 6, 7. So what used to be index 6 in the big tree, in this subtree is now index 0, 1, 2. So the index shifts. So we have to subtract half of, the number of elements in the tree divided by 2. So instead of I, we now have to I minus diff n2. Right. And of course, if we wanted to be like paranoid, we wouldn't want to divide by 2 twice, so we could make it a bit shorter, so we don't have to do this division twice. Right. And I think we never need this hash, actually. Okay. must forgive me, but I'm fanatical about indentation. Right, but the rest is basically the same. So now that we have recursively gotten the proof from the right subtree, so now because we went right, I need the left constructor here, tree hash of the left child, and this XS and A. Okay, that should do it, I hope. Did we have an example tree? No, we didn't. So let's make one. Oh, so example tree, Merkle tree string. So example tree is construct. So whatever, 8 programming languages. Haskell, Scala, Java, Python is 4. C, C++, 5, 6. Fourth, what did you say?
OCaml.
Like this? Yeah, I think, right. Okay, let's see. Example tree. Okay, that gets constructed. And we now see this additional parameter, so 8 elements. So that's looking good. And now we should hopefully be able to create Merkle proofs. So create proof. So of our example tree and index, so 0 gives us Haskell. I'm not sure about this left-right choice I made. So maybe I should do it the other way around. I think I don't know. It's completely arbitrary, but let's do it the other way around because then maybe I should, sorry, but I think it would be helpful to be able to visualize this. Maybe this is a waste of time, but I think it's also an important example. Okay. So indices, Haskell is 0. Haskell is 0, Scala is 1, Java is 3, 4, 5, 6, 7. Okay. So we combine Haskell and Scala, Java and Python, C and C++, Forth and OCaml. The next step is these and those, and then finally all the way up. So that's this example tree. Now let's look again. So let's do this 0. So Haskell index 0, and why is it now right? Did I not reload? Yes. So I changed right and left. So now the way you can read this is so you have to go left. That's the first left, left, left. So 3 times left, 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 and then you reach Haskell. And so this hash here, the first one must be, so we go left, and this is the hash from here. Then the second hash, we go from here left again, and this is the hash from there. And then the third, we go left again, and this is the hash from here, from Scala. So let's try another index. For example, if we want to go to, let's say, C, that would be index 4. So hopefully we get C as, yes, we do. And now we see right. So here we have to go right, left, left, right, left, left. That's correct. And let's try OCaml. So it's right, right, right. If we get to OCaml, right, right, right. If I try index 8, I get error called
in
index
the
out of
previous
index.
line.
Yes, here, index out of bounds. Okay, so that seems to work. So that's good. So now we have we can construct our proofs. So basically, if you are on a of course, you must imagine that there are, instead of 8, there are like 8 million data points in this tree, or 8 billion. So far too big to hold in your cell phone. So you use this service, I'm trustworthy.com, and you tell them to give you the second element in the tree, and that service says Java, but you don't trust them. So now, because they know you don't trust them, they don't only tell you the second element in the tree is Java, they also give you this proof. And now, of course, you need a way to actually check that proof, whether it's correct. So basically now we have to do proof checking. So check proof, or check Merkle proof. So given a Merkle proof, it will compute the Merkle root. So given a Merkle proof, it will give you a hash. Okay. Right. And then the idea is you compare that hash with the Merkle root you know, and if that's correct, then you're happy. Then the proof is correct. So let's see. And there are again two cases, namely that it's it's Merkle proof A. So if it's just the payload, so that means our tree is just a leaf. And in order to get the hash, then we must hash the payload itself. So in that case, it's hash A. And of course, that means I need the binary constraint again.
Would it make sense to provide the root and just return a Boolean?
It would, but I think to do it recursively, this is,
Okay, yeah,
I mean, we could do it like this.
right. Yep.
So binary A, so given the Merkle root, so the hash, and the Merkle proof, the Boolean, and then, so this would be the Merkle root, and then the proof, and then we would just call our other version with the proof and check that that's given the Merkle root we have. Right. The only problem is to do that in GHCI. Yeah, but it's fine. Right. Okay, so we can compute this. So in our case, in our example root of type hash would be, we have this tree hash of our example tree. I haven't implemented it yet, but we can already check this root. Our example tree was this, and our example root is just the top hash, so it should be this. Yes, so it's this top hash. Right, and then we could check a proof with, yeah. Okay, that's the easy case. So what do we do if we have like a left? So we went left, or the proof claims we went left. Some hash coming from the right, some other stuff, and our A. So in that case, we recursively calculate all the prime. We recursively call check Merkle proof on the proof where we have removed this hash. So Merkle proof XSA. So now we have the hash up to this point, and now we must combine it. So left edge means we walk left. So this edge here comes from the right. So that means we have to hash hash to byte string. So this h prime is then on the left because we walked left. So we have to combine this with hash to byte string h this way around. I think something wrong. Oh yeah, three pluses. Right. Okay, and now if it's a right, it's the other way around. So if we have a right here, then these two just have to be swapped. And that should be it. So let's see. So if we have an example proof, Merkle proof string, what was it called? Create Merkle proof of the tree. So our example tree, and let's say not Haskell because it's always going left, something like C. So index 4. So let's see, reload. So we have our example proof. It's this. And now we can do check Merkle proof prime first, let's say, of our example proof. Right, and that looks good because we do get the root we were expecting. So we can also use the check Merkle proof function without prime with our example proof and our example root. I thought we should. It's the other way around, right? It's first the root and then the proof.
Right.
Right. Yes, and that says it's okay. So Haskell is indeed, not Haskell, C is indeed contained in that tree. And now, yeah, I mean, how do I, it's a bit tricky to get an example. Let's see.
Maybe we can you want something wrong? We can create
Yeah,
a leaf with some other string and copy paste it.
yeah, exactly. So, I mean, this is like the valid proof here. And now I can do like wrong proof. So I just paste this in. And for example, if now I want to convince somebody that at this leaf, I mean, there with index 4, it's not C, it's JavaScript, the horror. What now? Oh yeah, that's ugh. The problem is this. Yeah, that's not read. I mean, the problem is now that this is not valid Haskell. So this digest is implemented stupidly.
Right.
Because you can't read. But it's fine. I mean, not all is lost. I can say let hang on. Let Merkle proof x as is example proof in Merkle proof x as JavaScript. Right, that works. So you can say wrong proof this. And now I have my wrong proof. I mean, it's of course only one example how it can be wrong. I mean, some of the hashes could also be wrong. But I mean, normally somebody would try to like cheat by claiming that that something else is in the tree. I mean, somebody, if in the example of blockchain where it's like blocks are the data, then somebody might want to convince you that he has more money than he actually has, for example. So he would cheat with the payload. Okay, and now if we do check Merkle proof, example root, wrong proof, we get false. So that detects that. Or, I mean, otherwise, I mean, if we use the primed version with the wrong proof, then we get a different hash. So our root is 76 something, and with the wrong proof, we get F8. So they don't agree, which shows that something's wrong. Yeah, so that's that. And as I said, yeah, sorry.
Yeah, I think that's it, right?
Yeah,
Yeah.
yes. I mean, as I said, there are like some refinements one could try to get it working for non-powers of 2, for example, or things like that. But I think it's actually fine like this. I mean, one simple thing we could do, I just thought of that. I mean, there are different ways how you can do it. As I said, one could, for example, use this, I mean, like enhance the tree type that it can also have nodes with one child instead of 2. Another thing I think you can do is just basically in this case where there's an odd number, I mean, basically put maybe things in the tree, in the leaves, and then fill them with nothings basically to get the full power of 2. I think there are various ways, but it's also not important. I think it's interesting, this idea. So I think it's a beautiful idea that it's very, very clever that you can basically verify a computation without having the data for the computation. I mean, I mean, abstractly what this does. And incidentally, there's also something, I mean, this is one example of these authenticated data structures, and there's actually a beautiful theory and that has been implemented in OCaml where you can also do more things. I mean, this is just lookup basically. We can look up elements at an index in this tree, and even if we don't have the full data of the tree, we can delegate this lookup to some untrusted party, and the untrusted party can give us the result and the proof, and we can verify that proof without having the data. And actually that can be generalized to almost anything. So whenever you have a recursive data structure like that, that can be generalized to many more operations, not just lookup. So in principle, one could also do like insert and things like that, or delete. So under other tree operations. And the principle would be the same, that the verifier only needs basically a hash or very, very little data, and he can delegate the work to somebody else, and that somebody else always gives him like the result of whatever operation and a proof. And the proof basically just consists of hashes, like a relatively small number of hashes, and then the verifier can like verify that the person who, or the party that did the actual computation did it correctly. So that's actually very interesting, I think. But yeah, the most prominent example are these Merkle trees. And I think it's a beautiful idea for this asymmetric computation. You can outsource computation even if you don't trust the person that does the computation, and be convinced that he did it correctly without having all the data. Okay, yes, that's that. And that's basically the end of this lecture. So this
No.
is just, no, it's not?
Yeah. Market tree code. Yeah, yeah. It's one, but I'm saying that there's no questions so far.
Ah, oh,
You,
okay.
you can keep moving. Yeah.
Right. So, I mean, there's just a summary. So again, so there are arrays in Haskell and vectors and that allow constant time random access, but be careful when you update arrays, then it might be much better to use sequences or maps. Or if you have to, you can reach for these mutable arrays. but normally you never have to. I mean, you have to far less often than you would think because they are very efficient algorithms operating on persistent data structures where you don't need mutable updates. Right, and there's serialization. Okay, and this was more like a case study now. I mean, the Merkle trees you probably never have to, or I don't know. I mean, these days people use them in smart contracts as well. So you
Yeah.
can also do this in Plutus in principle. So maybe actually if you write the apps on Cardano, you might need to implement Merkle trees yourself or at least work with them. And
Yeah.
also if you do Atala Prism also actually uses Merkle trees. So I think, yes. So Atala Prism, I think they don't store actual certificates on the blockchain. They basically have a Merkle tree of the certificates, if I'm not mistaken.
Yeah.
Could be wrong, but yeah. But at least go to and I thought it was just a nice case study because there are several things you can learn about practical Haskell, like dealing with actual in the wild libraries that sometimes use like don't have exactly what you need, or it's you first have to find how you use it for whatever you need, and often you have to juggle with several of these byte string types to, I mean, convert between lazy and strict, or like unwrap some encoding or base 16 or whatever. Right, and then of course the actual example. And we saw another example of smart constructors.
We have a question.
Yes,
In the group assignment, we have a data structure called try. Maybe you can
yes.
expand their significance in Haskell programming and instances where it can be applied.
Right, I'm not sure that's um what are they called again? Try what? Sorry.
What are the significance in Haskell
Yeah,
programming
yeah. I mean
instances?
the type. I forgot what it's called. Is it try?
Try. Tier
Oh,
I.
oh yeah, right, right. TRIE, right?
Yeah. You have it. We have it in the.
Yes, I know it's this assignment. Um, actually, I mean, I think it's just nothing Haskell specific. It's just a nice data structure. Um, try data structure. I'm just checking whether there's something on Wikipedia. So yeah, there actually is. Right. I mean, I just thought whether maybe they say what it's used for.
Implementation, no.
Or
Application.
yeah,
Full text search, web search engines, bioinformatics. Wow. Internet routing.
right. Sequence alignment. Right. I mean, I could imagine. Um, okay, so yeah, as you can see here, I mean, you also, I mean, I don't know more than you about this, but I mean, it seems they are quite useful, and it's just a, I mean, interesting data structure for certain applications. Um, okay, predictive text, autocomplete.
It seems like it's useful for like partial suffixes and prefixes.
Yeah, I suppose. Or if you have like a
Yeah.
sentence, I mean, sentences, for example, then I mean, if a lot of sentences or words share like a common prefix, then you don't have. I mean, if you like have a list of words, for example, just like or of names, like a phone book. Let's say a phone book. I mean, normally you would use map. I mean, one way to do that, a phone book in Haskell would just be to have like a map from a string to phone number. But then for each name, you would have like one node in the or one leaf in the tree, right? But a lot of names like have common suffixes, prefixes. So I mean, I don't know, you can be called Smith or Smithson or whatever. I mean, obviously, there's lots of overlap in names. And with try, basically, it's more compact in that case because you would, I mean, you have, I don't know. I mean, can't think of Johans.
I mean, autocomplete as well. Like you type the first
Yes.
and you can.
Yeah, sure. It can be just names. So whatever. Uh, just have to think of empty emerald. Enter by whatever, like this. I mean, you have like a word list for whatever purpose, like a dictionary or autocomplete or whatever. And normally, I mean, if you just use a map or a hash map or something, then for each of those, I mean, you would need one leaf, and you would, I mean, the string would be contained in each of these leaves. So you have one leaf apply, one enter, one emerald, one empty. Whereas in the try, because I mean, there's like quite a lot of overlap. I mean, in the try, it would be like, ugh, God, why? Uh, so you would like have the root. No, no. I think the dot is bad.
Yeah.
Come on, trigger.
No,
Not of,
you have to hit escape before like
yeah.
paint.
Okay, so in this case, I mean, something starts with an A and some starts with an E, and then we have like in our example, I mean, it's a bit silly.
Maybe we can add apple or something like that. So
Also not. Oh yeah. So we would have the L and then E and Y, and here we have the M, N. Finally, EM. Like this, right?
yeah,
Maybe, yeah, like this, sort of.
yeah, it looks nice.
Yeah, okay. Right. So I mean, you can see that it's probably more compact. I mean, here if you count letters, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27. So you would need 27 characters just for these keys. But here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I save 7 characters in this small example already. And you can imagine like that this would be much bigger if it's a full dictionary of English or something. So that's one reason, I think. So it allows, like for these string keys, I mean, in this case, it's strings, I mean, lists of characters, but of course, it could also be lists of gene sequences or something, of genes, with lots of repetitions and common prefixes and so on. So it's a more, I think, yeah, that's probably the main point, that it's more compact way of saving this. And also, I mean, you can have values on the way. I mean, there's also the case where you have I mean, if we had emptiness as well, is that with a Y or is it? No, that's with an I, right? For example, apples, then I mean there would be this, but the word apple is over here, so there would be a payload here of some kind here already, and then it goes on. So it's yeah. Anyway, that's like one reason definitely that try some more like memory efficient for things like this, for string keys in this example, especially if there are lots of common prefixes. So I mean here in apply one sees, so this APPL, because it's common to apple and apples and apply, I only need those for letters once. So I save space. Not sure whether it has other advantages as well.
Maybe the memory usage, because as soon as you go down just like 3 steps, you already reduce the search space by a lot.
Yes, probably.
Anderson says that understood, thank you.
Okay, great. Yes, I mean, we don't have much time left, but I think maybe I can at least start with semigroups and monoids, which would be the start of the next lecture. And they are very useful anyway.
Maybe a quick intro so they can start thinking about it.
Yes, exactly. I mean, there are two type classes that are very important in Haskell that we haven't mentioned yet, although we could have. One is called semigroup, one is monoid, and that's especially semigroup. I mean, both sound sort of intimidating, but it's something that we encounter. I mean, especially in mathematics very often, but also like in computer science. So it just, I mean, often we have something. I mean, let's just ask. So semigroup just has one operation, and that's this whatever it's pronounced, like smaller sign, greater sign for type A, and just an operation from A to A to A. And that's something that you have all the time. I mean, for example, addition on natural numbers. I mean, you add two numbers and get a number, or a concatenation of strings. So you have two strings and you can concatenate them to a third string, or in general lists. And there are lots and lots of examples of things like that. And it's all over the place. So Haskell has this semi-group abstraction for it. And we have talked about laws before, and semi-group only has one law. Semi-group law is associativity, which means that A, B, C is the same as A, B, C, which is quite a natural thing to have. And again, as with these laws, it can't be enforced by the compiler. So the implementer or the instantiator of this type class is responsible for checking this. And as we see here, if we ask for information, there are lots of instances. So in particular, lists, where the semigroup operation is concatenation. But okay, we don't see much yet, but in particular, we also see byte string is a semigroup, and it's just appending. So I could have simplified this example. I mean, I had this plus plus plus. So actually, I wouldn't need this. Now, of course, I get errors where I use it. So 35, sorry. So I can just use this semigroup operation, which in this case is concatenation. And where else do I get it? here and here. Right. And I mean, this works for arbitrary lists. So for example, I mean, we have always said Haskell plus Kenya to concatenate two strings, but the list instance for semigroup is just concatenation. So I mean, so you don't have to remember all these different symbols and what it's called, whether it's concat or plus plus or append or whatever. I mean, you can just remember this semigroup operator, and that works for all these cases. So now another thing is that, right. So that's that. That's semigroup, and it's only this one law, associativity, that it doesn't matter in which order you parenthesize the operation. And but semigroup is, I mean, it's all over the place, but most instances of semigroup are actually also an instance of monoid. So if we ask for monoid, then we see it has as superclass semigroup. And it has, I mean, you can forget about, because minimal is empty, so you can forget about mapend and concat basically. So memty, so just an element of type A. And that's the so-called neutral element. So if we have a monoid law is basically identity element. So that means that A that whether you like whatever I should pronounce it. I mean, if you the memty on the right or the memty on the left doesn't change anything. And most of the instances, as I said, are monoids. And memty is somehow a silly word for this, but I think it's because the mother of all monoids is lists. So list is in some sense like a universal monoid. And in the case of lists, this memty is the empty list. So it's like monoid empty. That's why it's called memty. So if we ask for memty type list of ints, for example, we get the empty list. And of course, if you concatenate the empty list with another list on the left or on the right, you get the other list. So it's indeed a neutral element. So in the special case of list of characters, aka strings, it's the empty string. So if I have Haskell and concatenate it with the empty string, of course, I get Haskell again. And so it's the same. Now, like a big like the circus of examples comes from numeric stuff. And I mean, we all know, like, for example, addition of numbers follows these laws. So for addition, we have associativity, and we have a neutral element. Also say neutral, which would be 0. However, for numbers, we also have like another natural candidate for monoids, namely multiplication. So multiplication is also associative, and the neutral element is 1. Multiplying by 1 doesn't change the number. And that's also the reason why in this list here of instances, we don't see, for example, int, because then it wouldn't be clear. I mean, then as I explained when we talked about type classes, a given type can only have one instance of a type class. So one would have needed to decide which to use, addition or multiplication. And the designers of the Haskell Prelude or base libraries didn't want to make this decision. So they didn't give an instance for int, for example, for monoid, because there are these two natural ones. However, what we do have is new types. So if I import, I think it's data monoid. And if I ask again for information, now there should be more instances. So we have this last and first. We can look at that in the next lecture. We only have 5 minutes left, but there should be something called sum and product. Or maybe that's in we also
They,
Yeah, here. So there's this sum and product. So if I ask for sum, it's just a new type wrapper around A, and we have monad sum. Sorry, no, we do, but it's not what I meant. Monoid sum, somewhere I saw it here. Here. So if A is a numeric type, then we do have a monoid instance for sum A. So basically, if you want like use monoid operations on ints, for example, as I said, it doesn't have an instance. So if I do 3 int monoid 7, for example, it complains that there is no semigroup instance for int. If, however, but I can basically pick one, for example, addition, by using this sum. So if I use this sum new type wrapper around my ints, then that does have a monoid instance, and it's so it also has a mempty. So if I ask for the mempty of some int, it's 0. And there's also product. So if I want the other natural monoid instance for numeric types, then I can do product. And then the semigroup operation is multiplication, and the neutral element is 1. And when I asked for information on monoid, I said only mempty is like new. Mappend is a synonym for this operator in semigroup. So instead of doing this, I can also say mappend. Again, that's historically because like the primary example of monoids is lists, and for lists, the monoid operation or the semigroup operation is appending to lists. So that's like monoid append. So this is just a synonym for this symbol here, for this operator. And finally, there's mconcat, monoid concat. So given a list of things, it combines all of them with the monoid operator. So if I have, which is, yeah, so if I have, for example, mconcat Haskell is beautiful, then it will basically apply this monoid operation between here and here. So for all elements of the list. And that, of course, then also works for things like sum 1 to 20. So it will sum all the elements in this list. And if instead I use product, then it will multiply all elements in this list. And I think beginning of next lecture, we'll briefly go over that again, and we see more examples. I mean, there are like in the standard libraries, first, last, endo. So lots of things in Haskell are monoids. So that's a very useful abstraction. Any questions? I think we're almost out of time.
Yeah, no questions. Nice speed run of monoid semigroup.
Okay. Yes, we will repeat that, I think, last next lecture at the beginning. But it's nice to actually have seen it before. And
Yeah.
maybe just one last thing. I know we are almost out of time, but because that's also mentioned in the next lecture. I mean, we have talked about the foldable class before,
Mhm.
and we said that I mean, it's basically container types that where you have two list operation. So you can extract if T is foldable, then if you have a TA, you can extract a list of A's from it. But actually, if you look here, and I have like ignored this until now because we didn't know about monoids yet. But actually, I mean, we have talked about fold R, that in order to implement by hand foldable, you can just implement fold R. However, you can also implement fold map. And if we look, and as I said, I have like neglected to mention this before because we hadn't talked about monoid yet. So that means if you have like a TA, so if you have a container containing A's, and you have a monoid M and a way to turn A into M, then you can turn this whole container into an M. So that's basically like a generalization of this M concat. So if this is lists, it would just be M concat. So what it does is it has this container of A's. It basically converts each of the A's into an M, and then it folds them all together with the monoid operation. So I mean, our tree type, is that still here? Yes, it is somewhere. Maybe not. Oh no, because sorry. Let me just go back to this model. I'm almost done. So here in this, so load more data structures. Right. So we had our tree type, and we know already that it has a foldable instance. So I can just and I can use this built-in support for that to get the instances. And now I have this fold map. So if I have our example tree, so one thing, for example, I mean, strings are lists of characters, so they are already a monoid. So I could do fold map identity with our example tree. So it would leave the strings alone. Identity of a string is a string again, and then wrap them all together with the monoid operation, which in the case of strings is concatenation. So so I just get all of the leaves smashed together, all the strings. But I can, of course, I don't have to use the identity. I must just get into another monoid. So for example, I could do some length. What now? Yeah, sorry. Right. So now it would, to each leaf, so Haskell Rust C, apply this function, so length of the string, and then in the sum new type. So we have Haskell has 7 letters, so that's some 7, some 4, some 1, and then add up the numbers. So that means all the leaves have together 12 letters. So just a brief introduction to fold map, because that's also relevant in the next lecture. So again, it basically maps all the elements in the container into a monoid and then smashes all of the monoid elements together using the monoid operation. Okay, I think we should stop here, except if there are any more questions.
Nope. I think we're
Okay.
good.
Okay, then we'll talk again on Thursday, right?
Yeah.
Okay, then.
Okay.
Thank you all very much. And
See you, everyone.
see you, everyone.
Thank you. Bye.
Thank you. Bye.
Bye.